Okay, time is 2:30. Let's begin here. So this is the last regular day of class. We will finish section 6.5 today. Our final exam is, of course, on Tuesday, May 5th at 3:30 in this room here. We will spend the last portion of the class reviewing for the exam. Are there any questions before we begin? Okay. So we were talking about the Placekicking data set once again, and we had estimated this particular model here, where we have the logit of the estimated probability of success for the kth place kick attempted by the ith place kicker. And we estimated the model. The x sub ik is the distance of the kick, and bi0 is a random effect. And basically what that random effect allows us to do is to take into account potential dependence within place kicker for these place kicks. And we had just ended up talking about, well, how can we what's called predict these B's? It's not too difficult, just involves maximizing a particular equation that has actually some integrals in it. And let's take a look at how R then can use those predictions. So if I want to estimate the probability of success, let's say I want pi hat for a particular distance, I can use, as you might expect, the predict function to do that. Well, there's two ways that you can use the predict function, and it corresponds to this argument here. So pi.hat.avg, that represents, I want to find the estimated probability of success for, let's say, an average place kicker. In other words, I'm going to set bi0 to be equal to 0. So that's what the NA means. Other than that, the syntax is essentially the same as what we saw way back in chapter 2. Now pi.hat.I now allows me, or what's in there is my estimated probability of success for, let's say, the ith place kicker. And so RE form, first of all, RE there, in case you didn't realize, this stands for random effect. And then form means how we're going to deal with the formula, you could say, for this random effect. What the null argument says, okay, let's just use the predicted values, let's say the B hats, for each individual place kicker when we actually find the estimated probability of success. And notice that my new data here is just the original data set itself, so the 1,425 observations. So I'm just finding pi hats for the original observations. I also do a similar thing for just finding the logit to pi hat, because sometimes comparisons on that scale is a little bit easier. So notice how I say type equal link there rather than type equal response. So I find all these these estimates, and I put them in a data frame called all, and here is the head of all. So let's focus on Stover here. For a distance of 20 yards, his estimated probability of success was 0.975. For the average place kicker, it's 0.972. For Kofer, for 20 yards, his estimated probability of success is 0.969. The average place kicker is 0.972. Since I'm looking at the average place kicker, that's why you see them equal at the same distance for the two different place kickers. Now, what I do some stuff here that I want you to take a look at on your own is I show how some of these calculations are actually made without using the predict function, just to for you to make sure that indeed that you know how the formulas are actually being used, how the model is being actually used. And at the end of the last class, I briefly introduced this particular plot here. what we have on the y-axis, we have the estimated probability of success. On the x-axis, we have the distance. The red line corresponds to, again, the average place kicker. So I say b sub I0 is equal to 0. And I just find the estimated probability of success. So I can use the curve function, as we've done many times before, to do that plot with the red line. Now the black lines represent lines for every single place kicker in the data set. I think we had about 34 place kickers in the data set, so there would be like 34 black lines there. And so what we can see here is a little bit of variability in these place kickers. At least what's observed, we see variability. The top line there that's separated from the rest corresponds to Al Del Greco, who was a very famous place kicker who played in the NFL for 17 seasons. And this was one of his best seasons overall. And through some code that you can see that I use in my program, I'm not going to go through the details of the code, you can see that in the end, he missed just 3 place kicks that in our data set here, and they were quite long. So he's doing overall really, really good. That's why we see Al Del Greco as that top line. I also have code in my program that shows how I can know that indeed that is Al, represented by that top line. Now the bottom line here corresponds to Chip Lohmiller. He didn't have as good of a career as Al Del Greco. He played 9 seasons, and this was his second to last season before he no longer was allowed to play in the NFL, I guess you could say. And you can see why his line is lower than the rest. So here's my good response variable, 0 for failure, 1 for success. And we can see for these distances, he's missing a lot of place kicks. And I mean, in fact, he missed 2 20-yard place kicks. No wonder he didn't last very much longer in the NFL. And so the reason why I point this out is because hopefully that allows you to get a better idea of why we see these lines here. Place kickers that are really good are going to be high. Place kickers that are low are going to be low. Or place kickers that are not doing good are going to be low on that plot. But remember what we've seen too when we looked at the let me back up a second. So what are what's the variability in these lines basically displaying in a picture format in comparison to a numerical format that we've seen before? What is the variability of these lines essentially representing? So each of the lines comes about through a different B, right? Okay. What measures the variability in the B's? Sigma squared. So, we go back to our model. That plot is basically giving us a picture of what this 0.0763 represents. So if that number was higher, what would you expect the effect on the plot? More spread out of those lines. If the number was lower, let's say if it was 0, what would you expect? The lines would all be right on top of each other. Okay? Now remember what we've seen before when we looked at the AIC comparing the model that had had the random effect versus the one that did not. The AIC was lower for the model that did not have the random effect. So while we do see some variability here, it calls into question if this variability is maybe just normal variability there, and that really it's not necessarily really significant, that there's really not that much. We're going to do some formal hypothesis tests later that basically conclude that too. Or it's going to tell us that there's not sufficient evidence to indicate that truly there are differences amongst these place kickers. Are there any questions? Okay, so let's move on to section 6.5.4, inference. Meaning I want to be able to do hypothesis tests. I want to do confidence intervals corresponding to the parameters that we have represented in our model. We are again using likelihood-based methods here. So because that I have all my likelihood-based methods available to me to do inferences, walled intervals, walled tests, likelihood ratio tests, likelihood ratio-based intervals. I have all those available to me. However, due to the added complication of this model here, some of the large sample approximations that we rely on, like a normal distribution for walled stuff, chi-square distribution for the likelihood ratio stuff, that stuff doesn't necessarily work as well as maybe it would if I didn't have those random effects in there. And so because of that, then I'm going to introduce to you an alternative approach for inferences, and this involves the bootstrap. We talked about the bootstrap a little bit earlier in the semester. Chapter 3, we did a hypothesis test for independence in a contingency table. Does that sound familiar? Everyone should be going, yes, I remember that. That was so cool when we were doing that. And basically, the idea that we did was this. We said, okay, let's simulate some data sets under the null hypothesis. Meaning, let's assume the null hypothesis was true. We had independence between the rows and the columns. Let's simulate some data sets. Calculate the test statistic for every single data set. Then you can say, do a histogram of the test statistics. And what that gives you is that instead of using like a chi-square distribution, instead we had a histogram that represented the probability distribution of our test statistic. Using now this kind of a probability, this representation of a probability distribution, we can find p-values, for example. Instead of using like a chi-square, we can simply use a histogram to basically fill the same role. And since it's not necessarily based upon, let's say, as n goes to infinity assumptions, this ends up actually working quite well. So we're going to do something similar here. Here's the general approach. Calculate the test statistic of interest, say W, for the original data using the estimated model under the alternative hypothesis. Okay. So let's put this into the context of the place-kicking data set. Let's say I want to test the following. So we're going to talk about hypothesis tests, and then we'll talk about confidence intervals later. With respect to the place-kicking data set, beta 1 was the slope on the distance variable. I want to test, is it equal to 0 or not equal to 0? So number 1 here says calculate the test statistic of interest for this. So what could I calculate? Well, maybe, how about we set W equal to -2 log lambda. Okay? Your usual test statistic that you would use for a likelihood ratio test. I'm not going to use a chi-square approximation to it, but I can still use the test statistic. Then, generate a large number of samples, which are called resamples in bootstrap terminology, using the estimated model that assumes the null hypothesis is true. These resamples should be of the same size as the original sample. So with respect to the place-kicking data set, I'm going to try to simulate data from my null hypothesis model, meaning the model that does not have distance in it. So I'm going to simulate some data from my null hypothesis model. So I need to estimate that model. And when I estimate that model, I can get pi hats out, right? We just talked about how to get pi hats. So what could I do with those pi hats to simulate a data set? How have we simulated data before when we had a binary response? 1.1. We use the R binom function. Okay, so what I can do is essentially, with the R binom function, I have all these pi hats for every single observation, assuming the null hypothesis is true. Put those pi hats into our binom and said, okay, go simulate 1,425 observations. And I'm going to get a bunch of ones and zeros out. It's actually even going to be a little bit easier for that. I'm going to introduce you to a new function that even simplifies that more. So I'm going to do that once. I'm going to do it twice. I'm going to do a large number of times. The reason why I want to do a large number of times is because I want to get a good picture of what that true distribution looks like. So what you're going to see in our example, we're going to do it 2,000 times. You can do it more, but if you do it less, you might not get a good, accurate representation of the distribution. Now, for each of these resamples that I get, so for each of these simulated data sets, what I'm going to do is basically, excuse me, I'm going to calculate my test statistic of interest once again. So I'm going to have to estimate my alternative hypothesis model, my null hypothesis model, to this simulated data set. Calculate a -2 log lambda. How about we call it -2 log lambda star to differentiate it from our original -2 log lambda. I'm going to calculate this for every single simulated data set. So how about I put a little subscript b there, and say we're going to do this from b equal 1. Oh, I shouldn't use b, excuse me. Let's use a different letter. We'll use a. I'm going to do this for a equal 1 to 2,000. So I'm going to have 2,000 of these W stars. So now that I have that, I can do a histogram of those, and it basically gives me a picture of what an estimated distribution should be of this test statistic if the null hypothesis was true. The reason why it's if the null hypothesis is true, because remember how I simulated my data? Assuming the null hypothesis was true. Now once I have that histogram then, so let me draw my histogram out again here. So maybe it looks like this. Not a perfect drawing. So I have all these W stars there. Okay? Now what I can do is look at my original test statistic value. Let's say it is W, or let's say it falls right here, my original test statistic value. Now note that that original test statistic value is kind of on the extreme portion of that distribution. So does that mean that this was a likely value to occur or unlikely? Unlikely. So if it's unlikely, what does that mean in the context of our hypothesis tests? I reject. I would have a small p-value. So we can quantify then the p-value as essentially the proportion of the W stars that are greater than W. This proportion would be small. If instead my test statistic fell right there, kind of in the middle of the distribution, that says, okay, that's a reasonable thing to have happen. So because of that, well, don't reject HO. I don't have evidence to say that beta 1 does not equal 0 here, because it's just reasonable to get a value of W like that if HO was true. The proportion of observations that are greater than W there will be kind of large. That's my p-value. So how do I calculate this proportion? This is what I'm going to do here. Note that I use a little b there. I used a above. This little b has nothing to do with the random effect. It's just an indexing measure. Maybe I should have used a or some other letter in the end to represent an indexing measure, but oh well. So let's say I have capital B total resamples. For us, it's going to be 2,000. And what this sum does here, it calculates the number of the W stars that are greater than the original W. So that I there, that represents the indicator function. We saw that back in section 1.1. So anytime that, let's say W star 1, if that was greater than or equal to 1, my indicator function is a 1. If it's less than my original W, W star 1 was less than my original W, then this indicator function would be a 0. And so because of that, it tells me what proportion of observations, then this whole thing there, what proportion of observations will be greater than my original test statistic. That's the algorithm to use. Are there any questions? Okay. Now we can also use the bootstrap to find a confidence interval as well for a parameter. So maybe, for example, you wanted to calculate a confidence interval for E -10 beta 1, which represents the odds ratio corresponding to a 10-yard decrease in the distance. So how do you do that? Same kind of process with some minor differences. Again, generate a large number of resamples using the estimated model of interest. So maybe my model of interest does have the random effect in there, and it does have distance in there. Then, for each resample, estimate the model and the statistics that estimates the parameter of interest. So here, E to -10, beta hat 1. So I'm going to calculate that maybe 2,000 times for 2,000 simulated data sets, 2,000 resamples. Then again, these statistics form essentially give you an estimate of a probability distribution for what you're after. And so what you could do, for example, to find a 95% what's called percentile bootstrap interval, is to take the 0.025 and 0.975 quantiles, observed quantiles from those 2,000 e to the -10 beta hats. The percentile intervals are not necessarily the best to use. Instead, a better kind of interval is to use what's called a BCA, which stands for bias corrected accelerated. And basically, this still finds particular quantiles from your distribution, but not necessarily 0.025, 0.975. It basically has some adjustment factors used with it that forms a better interval. I won't get into the details behind what those adjustments are. Okay, so let's go back to the Placekicking data set and do some inferences. So unfortunately, remember the little ANOVA function, the big ANOVA function, those cannot be used with fitting a model using the GLM-ER function for these generalized linear mixed models. So instead, we're going to do use some other mechanisms to get our test statistic, get our p-values. So again, I'm going to estimate my model of interest, but now this is going to be under the null hypothesis, where again, my null hypothesis is distance is not in the model. Notice for the formula argument here, you do not see distance at all, unlike what we had on Tuesday. So I estimate the model, and then to form my -2 log lambda statistic, remember I could rewrite this as -2 log, let's say the likelihood function under HO, the likelihood function under HO or HA, which then, again, using some math, you get -2 times the log of likelihood function under HO minus the log of the likelihood function under HO, HA. So there's a function R called log lick we may not have seen before, which allows you, not just with stuff from this from the GLM-ER function, but also from the GLM function, allows you to extract the log likelihood function, evaluate the parameter estimates. So that's what I do for the model under HO in the original model that we estimated on Tuesday, or last time. That's my test statistic. There's some odd labels that come with this, so I just use as.numeric to just take off the labels and just get the number itself, 238. I could have also equivalently defined this test statistic, use a function called deviance as well. basically finds the residual deviance for the two models and then subtracts them using the same kind of methodology that we saw in Chapter 2. Now, to do a chi-square 1 approximation, I can, if I do that, calculate my p-value the usual way. So notice how I'm putting in here for the q argument my test statistic, 1 degree of freedom, because I'm just testing distance. I get a p-value that's very, very close to 0. So there's strong evidence that distance is important. A little bit of a simpler way to do this kind of a test is that there is a function R called drop1, which means drop one variable at a time, do the corresponding hypothesis test with that. So if I do drop1, object equal mod.fit, do a use a chi-square approximation, put the results into LRT, I get output that looks very similar to what we've seen with the ANOVA function in the past. Again, a very small p-value. Let's talk about how we can use the bootstrap. So I'm going to set up for 2,000 resamples to resample from a particular model that you've estimated in terms of to generate new simulated data from a particular model you've estimated. There's a nice little function R that we haven't seen before called simulate. So if I say simulate object equal my model under the null hypothesis, how many different simulated data sets do I want? 2,000. Put in a C number so I can reproduce my results. I put the results into sim.h0. Now the format of what's returned to you is a little bit odd. So for the first simulated data set, I can extract that from sim.h0 by using a $sign sim_1. If I want to do the second data set, $sign sim_2, and so on. What will be a little bit easier for us, though, is if we look at a different way that we can extract this kind of information. Note, whenever I use a $sign there, that means I have a list. So another very general way to access components of a list, one by one, is to use that syntax there. Sim.h0, bracket, bracket, let's say I want the first data set, end bracket, end bracket. And that's going to extract out that first component of my list. If I apply the head function with it, look what we get. Ones and zeros. Our Bernoulli observations, you could say. Next, using the bootstrap can take a while because you're doing basically a Monte Carlo simulation. And so I'm going to keep track of how long it's going to take me. So I ask R to tell me, basically, what time is it right now by using proc.time. I put the results into an object called start.time. Then I create an object of actually a vector, lrt.star, which is going to allow me to put all my -2 log lambda stars into it, all 2,000 of them. To then estimate the model and calculate the test statistic for each of the simulated data sets, I use a for loop, which we've seen in the past. So I'm going to do for I in 1 to the number of resamples I have, number of simulated data sets. Use the glm-er function, as we've seen before. Notice my response variable is the ith simulated data set, ith simulated set of Bernoulli observations. I'm estimating my model under the alternative hypothesis. And then I can simply use the drop1 function to calculate my test statistic of interest. And I immediately pull out my -2 log lambda star. I put that into the ith component of lrt.star. Let's look at a histogram of all these 2,000 lrt.stars. Here we go. On top of that histogram is a chi-square 1 approximation. So what do you think? Does a chi-square 1 approximate the distribution of this test statistic well? Yeah, it looks like it does. So I would expect very similar p-values from using the bootstrap and using the likelihood ratio test. To find then the p-value, I take my vector of all my LRT.stars. There's 2,000 things in there. I look at how many are greater than the original test statistic value, and I want a proportion. So in other words, I want a mean of all my ones and I want a mean of what are created as ones and zeros for is LRT star greater than test statistic, and I get a p-value of 0, indicating again strong evidence against the null hypothesis. How long did this take me? This was on my surface, about 21 minutes. So you can see it takes a lot longer than just simply using a chi-square 1 approximation. It's just the way it is. Okay. Any questions?
I have a question.
Sure.
Would you still get some sort of a good idea if you didn't do 2,000? If you still have to have like a lot.
Well, you need a lot because what you're trying to do is get a good approximation of the distribution. You know, think back to your very first stat course when you learned about how to simulate a data set from a normal distribution. If you had 10 observations, it may not be a nice mound-shaped histogram. If I have 100, it's going to look better, and so on. So the better, the more, the better. Obviously, there's you could say the law of diminishing returns comes into play. You know, is 10,000 going to be really better than 2,000? Probably not. And the reason why I did that much is because notice where we're often looking for p-values, out here on the edge. And so I want to have a lot of information there on the edge, or the tail of the distribution, so I can get a good idea of what that p-value is. So that's why I chose as much as, let's say, 2,000. I wouldn't typically go less than that. If it would have took less time, I probably would have took 5,000. So what about a confidence interval then? Well, let's first of all, we're going to look at a confidence interval for the odds ratio. So I want a confidence interval for e to the negative 10 beta 1. And so then the estimate of this then, so e to the negative 10 beta hat, comes about through extracting the corresponding beta hat 1 value from my mod.fit5 component. And remember, we looked at how to do that in the past. Remember, we had to, or last time, we had to use the @ symbol there instead of the $sign. And so if you do the calculation, then you get 3.21. So what that again that says is that the estimated odds of a success are 3.21 times larger for every 10 yard decrease in the distance. Now, this is also conditional on, please understand this. This is a little bit different from what we saw in chapter 2. It's conditional on, you know, that you're talking about, let's say, the same place kicker. Okay? So please make note of that. And I made a little change in my notes on page 30 relative to that. It's not necessarily for the average place kicker. It's true for the average place kicker, yes, but okay, so how can we do a confidence interval? Well, let's do a walled interval first. I can use the confident function. My model fit is in mod.fit5. Now, if you remember back in chapter 2 when we first looked at the confident method functions for the GLM, using GLM, we could specify a name of a corresponding explanatory variable. We can't do that here. Instead, you have to specify, let's say, the numeric position. Notice how this beta hat 1 was the second one. You have to specify the numeric position in the vector of your betas, you could say. So it's the second one, 95% interval. I want a wall. And so this is what I get. This would be then for a 1 unit increase in the distance. I can then, similar to what we've done before, change that to a 10 unit decrease, and here's my confidence interval for the odds ratio. What about profile likelihood ratio intervals? You could do that as well. We use confint again. The only difference is that we use method equal profile there. Note that the syntax is a little bit different here from what we saw in chapter 2 with respect to this method here. So I did that. I was kind of surprised to see this occur. Look at that interval compared to the one that we just got up here. You know, the first time I ever did this, I was like, wait a second, what's going on here? Is there an error here? Yeah, there is. If I change the parm argument to 3, oops, actually this, sorry, just to make sure you're looking at the right comparison here. Sorry, I should be comparing to that one right there. Right? Yes. Okay. So I played around with it, and I did parm equal 3. Now notice what I get from my confidence interval. Very similar to what we had with the wall, which is what I would expect because I have a large sample size. So you got to be careful using this. Even though it is the second, and if you look at the help corresponding to this function, it says the order in that beta component of that object, that list that you're getting from glmer. It should be the second position, but here it was actually the third. So be careful about that. Okay, let's see here. So what's interesting too is the confident function is actually a method, corresponding method function for this. It allows you to do bootstrap intervals too. So you could do percentile, you could do the BCA interval that I just talked about. Unfortunately though, and I haven't been able to figure out why, the function only works when you're using a quadrature with just 1 point. If you do anything more than 1, we actually, if you remember from the last time, we actually use 5 points. You get an error message. It doesn't make sense to me why that would occur, other than maybe it's preventing you from using so many points, because you have to realize that this model has to be re-estimated, in this case 2,000 times. And of course, the number of more points of quadrature you have, the longer it's going to take. And so perhaps that's why they never decided to program it in, so that you could use more than 1. But it doesn't mean that you can't do it. And so what I did was I actually included some code for how to do this calculation with having the 5 points of quadrature. And I get an interval for a BCA interval of 2.7 to 3.79. Now the actual computations or the formulas that are involved for this BCA interval, I think it's kind of a little bit beyond this class. If you want to know more about it, take Computational Statistics 1 in the future. Well, what about, let's say I have maybe a lot of confidence intervals that I want to find, or maybe I have some confidence intervals for odds ratios that involve, let's say, interaction terms or quadratic effects. Now in those cases, it gets a little bit more complicated, and what we would do in that situation is use the MC profile package. Fortunately, MC profile doesn't work with these generalized linear mixed models. So instead though, what we can do is walled intervals using a package called multcomp for multiple comparisons. I don't think we talked about that in this particular class. It's actually introduced in an exercise of chapter 2 in the book if you want to know more about it. Excuse me. And it works very similar to MC Profile. The reason being is because actually MC Profile borrows stuff from multcomp. Multcomp is a package that you're going to have to download yourself. And so after I do that, I say library multcomp. I need to find my K matrix as we've done before. That allows me to find a linear combination of my betas. So for the confidence interval that we're interested in is a 10-yard decrease in the distance. So notice how I have a 0 for my coefficient on beta 0. I have a negative 10 as my coefficient on beta 1. Just to illustrate how this function, how this package works, I decided to throw in another linear combination as well. So 0 times beta 0, 1 times beta 1. So I have two linear combinations I'm interested in here. Then I can use the GLHT function to work in much the same way as the MC profile function works. So I put in my model fit information for the first argument, and then for my my coefficients on my linear combination, I use the LIN FCT for linear function argument. I put in K. To find my confidence intervals, I use the confident function with the resulting linear dot combo, as we've seen many times before. I want 95% intervals. In this last argument, you have to be very careful about, because it is different from MC profile. I want two 95% intervals. By default, this particular function will do some adjustments, such as like a Bonferroni correction. It doesn't actually do a Bonferroni here. I don't remember exactly which one it uses, but it does those kinds of corrections to control the family-wise error rate. For the demonstration purposes, I don't want those corrections at all. And to avoid those corrections, you can say univariate C alpha parentheses and parentheses. It actually calls a particular function that says, okay, don't do any kind of corrections. So what this gives me is my confidence interval for the log odds ratio. So for a 10-yard decrease in distance, my confidence interval is 1 to 1.33. I can work with this some more and use the EXP function with it, so I can find intervals for e to the negative 10 beta 1. And I get 2.72 to 3.79, which is exactly what we had previously using the confidence function, and when we said method equal wall. Are there any questions? Okay. So, to finish up here, what we like to do now is look further into this random effect. Do I truly need a random effect for this particular situation? We looked at the AIC as a way to do that. Do note that often in general, the AIC can favor a model that does have the random effect in there. Okay? Although the AIC didn't do that, or obviously concluded here that we didn't need it. So an alternative way to approach this problem, other than using the AIC, is to do a formal hypothesis test. Specifically, I want to know, for let's say the Placekicking example, I want to know, is sigma squared b0 equal to 0? Which says, okay, don't need the random effect because the b's don't vary at all. Essentially, each Placekicker they're identical. Versus sigma squared b0 is greater than 0. That's my hypothesis test. Since we are using since we're using likelihood methods, we could use wall test. We could use a likelihood ratio test as well. Unfortunately, though, the distribution of the estimates of this sigma squared here is very highly skewed. And remember, the Wald uses a normal distribution approximation. So you can see that that could cause issues, problems with using the Wald tests and to get accurate inferences. With respect to the negative 2 log lambda statistic, a likelihood ratio test, you could use that here too. The problem is a chi-square 1 approximation doesn't work well. Instead, what you can do, what has been shown to work well instead, is to simply divide the p-value by 2. So use a chi-square 1 approximation, divide the p-value by 2. Simply implement. We can also use the bootstrap procedure too. So in a very similar manner as to what we just got done talking about when we did a test for distance, we could do a test for sigma squared here. take resamples under the null hypothesis model, let's say 2,000 of them, calculate -2 log lambda for every single resample, and look at the -2 log lambda for our original data, look at its placement with respect to the distribution that you're simulating. So let's take a look at how to do this. So the likelihood ratio test using a kind of a chi-square 1 approximation. The model under the null hypothesis does not have that random effect in there. So because of that, I can just simply use GLM to estimate that model. I can then form my likelihood ratio test statistic in very much the same manner as we did a few minutes ago. I get a -2 log lambda of 0.653. My p-value, using the divide by 2 method there, is 0.2095. So there's not sufficient evidence to indicate that indeed sigma squared is greater than 0. So what this is saying to me is that there's not sufficient evidence to indicate that a random effect is needed. How about using a bootstrap with -2 log lambda? The code you can see on your own. It's very similar to what we just got done doing. P-value 0.16 about. Notice how that's close to what we had with using that chi-square 1 like approximation. So that's interesting. Here is then a histogram of the -2 log lambda stars. The red line there is a chi-square 1 approximation. Notice chi-square 1 does not work well. You know, if I use a chi-square 1, what would have been my p-value? About 0.4. And so you can see why it wouldn't have worked well. This is a little bit too far to the right, that red line is. The blue line here represents my observed test statistic, and you can see why, and indeed I did not reject HO. Because it's in an area where there's a sufficient other, or there's a kind of a larger probability. Okay, so some final comments then with respect to this section. Generalized linear mixed models are great things to have whenever you have some kind of dependence in your data in the formats that we've just talked about. The problem is it's not necessarily a cure-all for all situations. In particular, one of my own research involved this choose-all that apply data setting that we talked about last time. In that particular setting, I can actually have negative correlation amongst my binary responses to each, let's say, item on a survey. And generalized linear mixed models, the typical kind, cannot handle that. They actually assume a positive correlation. And lastly, another way to handle dependence amongst the responses is talked about in section 6.5.5 using things called generalized estimating equations. Just a little bit of a different way to look at some of these issues. Okay, so that completes section 6.5. Are there any questions? Okay, let's spend some time now reviewing for the final exam. First of all, the stuff in section 6.5 is not on the final exam. Okay? Since we were doing it right at the end of the semester, we didn't necessarily have like another class period available where you could ask questions about it, and to for you to have also to have an opportunity to go through the homework. I mean, I do have homework online for it. You're welcome to take a look at it, but it's not going to be on the test. I hope you're not disappointed. So I'm sure all that bootstrap stuff, you were hoping that you could do it on the test. And wait 20 minutes while the computer gets done so you get a p-value during the test. So the test, of course, again, is Tuesday, 3:30 to 5:30. There's going to be a little bit of a different format to it than what we've had before. You will not need to use the computer here. To help you out, what I've basically done is did the computer work myself, and I will give you some code and output that you can look at during the tests. Now, what that might mean, though, is that maybe I say, okay, estimate a model, whatever model. Okay, I might, let's say estimate it 2 different ways, and you need to know, well, which way was correct. And based upon then what you see from the output coming from that, you can write the estimated model on the test. Okay, so hopefully that will help you out on the exam. Now you do need to bring a calculator, though. There will be some very small portions, like maybe you need to take e raised to the negative 0.2 power to do like an odds ratio. Okay, there are a few of those really small calculations. So bring a calculator for the exam. Please make sure you don't have other things that you shouldn't have on that calculator that would help you out on the exam. Just simple calculator. Now the test is not finalized yet. I think final exam week kind of just crept up on me really quickly. A few weeks ago I had put together a rough draft, and I haven't had a chance to come back to it. I think it's in pretty much the shape that it's going to be in, but there could be some minor changes. What I can tell you with the current format right now is that with respect to the test number 1 and number 2 material, there are 73 points that I have assigned to it. With respect to the material after test number 2, so that would be just chapter 5 for us, there's 27 points. Again, this might change a little bit, but it should be about that. I have purposely tried to go, excuse me?
Number 2. Test number 1 and 2 from the previous.
It says greater than test.
Greater than. 2. Yeah, that's a greater than sign there. So after test number 2, that was my little shorthand. I purposely have tried, and I purposely, I should say, I've done this, put questions from every single chapter that we've covered on the exam. So don't just say, okay, I don't have to worry about chapter 1. I wouldn't do that. There are questions on chapter 1 on the exam, questions from chapter 2, questions from chapter 3, and so on. That's why this is called a comprehensive exam. There is an extra credit problem on the exam. I've actually posted it as kind of a take-home extra credit problem. I don't know if I've ever done a take-home extra credit problem before. It's take-home, but that doesn't mean you don't talk to other people in the class about it, okay? This is just for you to do. And basically, what you can do after class is you can download it from the Graded Materials webpage, and then you can type in your answer, print it off, and bring a paper copy with you to the exam. Make sure you put your name on it and hand it in with your exam, okay? I just want to briefly talk about the extra credit problem. So, all of you should have seen this already. This is the cover of my book. It's kind of a unique cover for statistics books. Typically what you have is some cool looking plot on these covers. And so there's a little bit of a story behind this. Back when I was finishing up my book, my publisher said, okay, why don't you submit some ideas for covers? So I submitted 3 ideas. 2 were of the traditional format, using graphs. So for example, if you remember my my plot in chapter 2 with the Placekicking data set, we saw the estimated probability of success versus the distance. We had some nice bubbles on it and so on. That was one of them that I had submitted. And I did this 3rd one as based upon some stuff that my editor that I had worked with CRC Press really liked about the book, was that there was tons and tons of different examples, and they covered a lot of different areas. And I thought, okay, that might be a good selling point. So how about we try to somehow represent these examples and other stuff in the book by creating a collage of pictures that kind of represent what this book is about. And so I submitted this cover idea to my publisher, and I said, this is just an idea. I would assume that your graphics editors could probably do a lot better job than I could, and I'd be happy to work with them on it. And so, my book was published like about August 1. And this was like in March, I think, or April. Didn't hear back from the publisher much, or I didn't hear back from the publisher at all about the cover of the book. It was in June, and I got an advertisement for CRC Press books, and what do you know, mine was there, and they had the Placekicking data set graph on it. I thought, oh, okay, I guess they chose it. I wish they would have told me that, but okay, whatever. Then, just like a few weeks before it was published, the book was, then I was actually given what the actual cover was going to be, and they chose this one. Exactly this one. The exact one that I had sent to them, which I said was, okay, this is kind of like a prototype. This is how you could, perhaps how you could do it. And if I would have known that they were going to choose this one, I would have probably done a few things a little bit differently. I mean, it's a nice cover. But I would have made some stuff a little bit nicer. But anyway, the whole goal, I guess, really was whenever you go to like a conference, like a STAT conference, for example, there's a lot of book publishers there, and they will have their books arranged on nice tables and stuff. And I wanted my book to stand out so that when people are walking by, they say, "Oh, that's interesting." And so I don't know. Maybe that's what's helped sales. Maybe not. So that's the story behind the cover. And what you can see there is that there's essentially 9 different pictures. Here's the actual thing that you can download from my website for the extra credit. There are 9 pictures. There's a little diagram showing the pictures there. For extra credit, I want you to identify what example, what program, what set of lecture notes that all 9 of these correspond to. Okay? A lot of these are going to be easy. I anticipate that there's going to be 1 or 2. It might be a little bit more difficult. So just simply type in your answers here, and do note, and I can do this especially since it's extra credit, you need all 9 correct.
How many points is extra credit?
I haven't decided yet. So, I mean, it's going to be worth your while, so. Anyway, yes.
There's actually a small picture of you between
Okay, yeah.
5 and 7.
Thank you for bringing that out. Okay. So this small picture, don't think of that small picture as a separate. It's actually contained in that whole, if you see where my mouse is, that whole, the larger one. Okay? Hopefully it will make sense what that is coming from, if you've ever looked at parts of my website close enough. So anyway, that's the extra credit. Are there any other questions about it?
So what should we write down for the title?
Well, for example, if you see one that deals with the Placekicking data set example, well, put Placekicking data set example. You might want to cite particular page numbers if needed. Enough information that it's going to be obvious what I know what you're talking about. Okay? I was really happy as a native Nebraskan that I was able to get this picture right here on the cover of the book. I had to actually ask permission from the athletic department office for that. Because if you notice, there's the N there, and that's a trademark, or it's a trademark of the university. But being a native Nebraskan, I was able to get that on there. Okay, so let's see. So let's continue with the review then. Now also I will give you those same formula sheets and that R code sheets that you've had before that's been, you've had access to a PDF. I will give you a printed copy of those pages. And I've added stuff for Chapter 5 as well. So you'll still have access to my formulas and R code, even if you're not typing R code now, obviously, but you still will have access to that. You just have it in a paper format. Now, after I grade the exams, I will post a message to the listserv saying, hey, I have graded the exams. You can go to Blackboard and take a look at what your grade on the final exam was, what your percentage grade for the overall course was, and then also what your overall letter grade was. Now, shortly before this class, I actually posted something to the listserv too regarding what is your current status in the course. So please make sure you take a look at that. If you see any errors, let me know. That's why I do it now versus wait until after the finals. Okay, so let's get errors corrected before I finish up with final grades. So again, once the final exam is graded, I'll post a message to the listserv, say, hey, everything's graded. I'll talk a little bit about what happened on the exam in terms of what maybe was a difficult problem or not, and I'll say, go check your grades. If you like to talk to me about your grade, or if you like to see your final exam, set up an appointment with me, and we can meet. I strongly recommend that you set up an appointment rather than just stopping by my office, because since it's final exams week, my schedule is quite off. Okay. Let's see. So let's. Any questions about the format of the exam before we do a little bit of a review of the material? Okay. So with respect to the material that was in chapters 1 through 4, what I would tell you is basically what I told you before. In past test reviews. So I recommend rewatching those videos. With respect to chapter 5 then. So the first thing that we started talking about was variable selection. How, often you're given a situation where you have a number of variables, explanatory variables. You don't know which ones to include in the model. And so what we talked about was some techniques that one could use to figure out which variables to use. And most of them will rely on looking at information criteria, such as the AIC, such as the corrected AIC, such as the BIC. Make sure you know how to calculate them. Make sure you understand the comparisons between them. Which one will end up with typically a larger model. Then once we have that numerical mechanism that allows us to compare models, we need to figure out, well, which models to compare. And so we talked about something called all subsets, which the goal is essentially to look at all possible models that one could have, subject to the limitations of maybe you're just looking at main effects, maybe you're looking at main effects and interactions. Look at all possible models. The model with the smallest information criteria is the better model. Since the number of models might be a lot, we looked at alternatives to that. We looked at specifically the genetic algorithm, which allows you to instead of looking at every single model, allows you to try to find that best model. Unfortunately, though, this method is stochastic in nature, meaning that you might not necessarily get the same model from one implementation to the next. So that's why we set a seed. We said, try to use this more than once to see if you get something better. Then also we talked about stepwise selection methods. Of the 3 methods here, this is probably the worst of the 3, but it still can end up providing a good model. And stepwise is easier than the other 2, and sometimes maybe that's the only thing that you can do, as we kind of saw with the Placekicking data set. And then also we talked about using model averaging. Instead of just picking one model, maybe you could actually have multiple models and essentially kind of average over them to get a better idea, a better understanding of your data set. Also, this model averaging set of methods also provide you a way to pick one overall model. So if you remember, we were given an approximate probability of a particular model being the best. Once we do that, then we need to, let's say, look at, assess the fit of the model. So we looked at a variety of measures to assess model fit. How good is the model estimating the data? And so we looked at, first of all, ways to detect, let's say, poorly fit observations, meaning maybe we have outliers. And so we looked at, let's say, Pearson residuals, and also the standardized, I can't write, standardized Pearson residuals. Make sure you understand how they come about, how to interpret them. They're a little bit tricky to interpret because we can't just simply use a normal distribution, standard normal distribution approximation with them. Make sure you understand why you can't just simply use a standard normal distribution approximation with them. Now, before we even calculate these residuals too, when we were dealing with binary regression models, we said that you should put the data into explanatory variable pattern form. Basically, convert a data from a Bernoulli format to a binomial format. Make sure you understand why one should do that. What are the benefits to it? Also, make sure you understand, well, when it's not going to work out. When explanatory variable pattern form doesn't really provide any benefit. We had a lot of nice plots starting on page 540 in the notes. Because often with these kinds of residuals, we want to plot them so we get a general overall view of what's happening with particular observations. And we looked at particular patterns that could have happened, or particular, cases where maybe a lot of observations were kind of pass or plus or minus 2 or 3 lines. Make sure you can understand and interpret those plots. Then as an overall measure of just how good the model fits the data rather than one observation at a time, we looked at goodness of fit measures. And we focused on this deviance divided by the degrees of freedom. And we said if it was greater than 2 or 3 standard deviations from 1, that says, okay, maybe we have a model that's poorly fitting the data. Make sure you understand why we're looking at the number 1 and why we're looking at 2 or 3 standard deviations. Then we went into talking about the influence of particular observations. We looked at, for example, the delta x squared. We looked at Cook's distance. We also looked at some other measures too. Make sure you understand how to interpret them, how to identify particular observations that are potentially influential from looking at those measures. We also had a nice little function that I wrote for you to simplify your lives. Actually, we had a few of them. In particular, we focused a lot on one of them, examine.logistic.reg. Remember, we gave you 4 nice plots? Well, maybe what I could do on a test is run the function for you. Here are the plots. Interpret them one by one. Tell me what they say about my model. And then I could ask you, okay, what should I do next after I got these plots? Then we talked about one specific problem that sometimes happens. You have overdispersion. That basically means that you have more variability in your data than what the model says you should. Well, make sure that you understand, how to detect it, and then what to do about it. I gave you a list of 5 things about what you could do about it. We've actually talked about all 5 now. We focused in this particular section on 2 of them. A quasi-Poisson or quasi-binomial model. And with respect to count responses, we did a negative binomial model. We also talked about the beta binomial model as well. It's okay with me just for you to focus on overdispersion with respect to, in terms of the solutions to overdispersion, focus on the count response stuff in terms of the quasi-Poisson and negative binomial. So I'm not going to ask you a question about beta binomial. I'm not going to ask you a question about a quasi-binomial. It's good to know that stuff, but you just don't have time to do everything. So make sure you understand how to estimate these models, how these models try to take into account overdispersion. Make sure you understand why these 2 approaches should be kind of more of a last resort, rather than the first thing you should go to if you have if you have overdispersion. And make sure you understand those case studies in section 5.4. We went through the logistic regression placekicking data set case study. There was another case study as well in section 5.4. Make sure you do read it. Okay, so that's all I had to say specifically about the material to review. Sorry I went a little bit longer than I had anticipated. Are there any last questions that you want to ask in class, or you can always ask them via the listserv too? Yes.
I'm just kind of curious, is there a variable selection procedure for mixed models?
Well, one of the issues with mixed models, and you see this in 971, you often have a designed experiment. And if you have a design experiment, and let's say the pigs in a pen example, you're going to keep that pen in the model no matter what.
Right. Okay.
Now, in terms of, like obviously with the placekicking data set, do we treat then the placekicker as a random effect or not? Fortunately, there's just one thing to consider there. So, you could do the hypothesis test. You could look at the AIC as a way to make that judgment. In terms of, let's say, maybe you have a number of different random effects to consider, and you want to maybe use a function like GLM multi. To be honest, I have not tried it. I bet you could get it to work though, because that function is quite general in that you can program it to do extra stuff than beyond simply, using models fit by GLM. But I really don't see a whole lot of model selection amongst in a situation where you have a lot of random effects. I don't know, do you talk much about 971 about that?
No, I mean, I didn't think it was really a thing either. I was just more curious.
Yep. Yeah.
Obviously, if you have a random effect, you should probably keep it if it's part of the design. But yeah.
I mean, it's often you're doing the model selection typically more so on the fixed effects, if it's not necessarily a design experiment. Yes.
Could we bring the formula sheet to the?
Well, no, I'm going to give it to you. Sorry if that wasn't clear. I'm going to print off copies and give it to you during the test. Okay?
Another question.
Sure.
For the model averaging method.
Yes.
To the verbal selection, is it specific to Bayesian method?
Well, I mean, there's some underlying Bayesian methodology behind it. I mean, obviously, we didn't necessarily talk about that aspect. You're not responsible for it. Rather, just focus on, stuff about, those weights, those model weights, and how they kind of represent then the probability a particular model is better. Okay.
So what's the difference between the Pearson statistic and
The deviance.
the residual deviance?
Okay. Residual deviance is solely based upon a negative 2 log lambda statistic. Okay. A Pearson statistic is based upon, let's say your observed value minus what you expect under the null hypothesis squared divided by expected summit over all observations.
But the deviance, residual deviance is also the observed, the mode of interest minus the saturated.
Saturated.
Yeah, the saturated is
So-
similar as the observed when they are fully, the parameters are fully.
Okay, so so residual deviance. You're basically doing a hypothesis test. HO is your model of interest. HA is the saturated model, which says, okay, just use your observed values. Note what a Pearson statistic is doing. If you actually look at the numerator, you have a residual there. What your observed value is minus what you expect under the model. So you're testing the same hypothesis. You're just doing it in a different way.
So that do those two.
Let me back up. Are you talking about like when we're doing modeling, the residual deviance in the Pearson statistic, or are you going back to? I guess you're not. Never mind. Go ahead.
So chapter 5, if the output of those two values, are they always telling the same results, or they may be different?
They are trying to test the same thing. Very often they will be very similar. There are cases where they can be a little bit different. In particular, I have actually seen it with the Placekicking data set because the way, if you look at the components of the residual deviance in the Pearson statistic, they're based upon individual residuals, essentially. And some of those, if you look at the model, I believe it's a model just with distance in it, some of those, we had some very large Pearson residuals, and I think they're either a lot larger or a lot smaller if you look at from the deviance residual point of view or the Pearson residual point of view. And because of that, the two overall statistics are actually a little bit different. So yeah, they can actually come up with a different conclusion, yes. It doesn't happen often, but I have seen it happen. But I would never look at only those two. I would not only look at, let's say, one of those tests overall to make a decision. Okay? We are actually out of time. If you want to still ask me questions afterwards, please feel free to do that. But we are done here. Thank you again for taking the course.